Okay, I will present a joint work with Neil Camardella, who is a PhD student with Sean Mine at University of Florida, and also with Sean that is here in the audience, and also Yunting is a postdoc at Stanford, working with Ram Rajagopal, and Cheng did a postdoc at INRIA and now is researcher at EDF. So I will talk about distributed control of flexible loads, and I will start with giving a short overview of our previous research, and with focus on the simplest possible control solution that turns out to be very useful in practice. And then our main focus of the talk will be on optimal control formulation for distributed control of flexible loads. Here the first, second and third section will be sort of a tutorial to give you idea and set the notation for the approach, and then the main part is in section 4 and 5. So we will concentrate on optimal control using the cost formulation that is based on Kurbel-Leiber quadratic cost. And well, goals have been already very well presented in a talk by Johanna Matthew, and it is very similar. We have a big population of flexible loads. Think of residential loads, and to fix the ideas, think of water heaters or fridges, so any kind of loads that have thermal inertia and therefore can provide storage to the grid. And objective will be to modify the power consumption of the ensemble of the loads in order to track a given reference signal that will be defined by the applications that we want to study for the flexibility of loads. Main approach uses mean field models, and so it's based on theory developed by Lyons and separately by Peter Keynes, and that was brought to power systems community by Roland Mallarmé in the 80s already, using the models for water heaters. Okay, so a bit more details. So we will have residential loads, and just think that these are simple on-off loads. So we cannot really have continuous output of a single load. But if we look at large population of these loads, then our goal is to modify their behavior in order to track some signal. And this signal can be either online or offline. And so by online, I mean that you actually don't know the signal in advance. It is given to you point by point. Think of it at every couple of seconds, every couple of minutes. It depends on the balancing area you are studying. And so typical application of these ideas is frequency regulation or balancing reserves. In that case, we will have online signal that is given to us in real time. But you can also think of applications to load shaping, and in that case, you might have some forecast, and so at least part of your signal will be given to you in advance. Okay, so we like to call this approach demand dispatch. So it is not given, not defined by price signals, but actual direct control. And the other important ingredient is that we only use inherent flexibility of the loads, so without consumers having to decrease their power consumption and impact their quality of service. So basically think of it as moving their power consumption across time. Right. And the idea is to put as much as possible of the decision at the local level, and this has two benefits. First is at the individual load, you can measure quality of service. Typically, if you have an air conditioning system, you can measure the temperature inside of the house, and you don't need to send this information across I don't know, to some centralized entity, so it also preserves your privacy. But on the other side, it also means that most of the intelligence has to be put on the local level, and so in general, we will assume that we only receive a scalar signal that captures the needs of the grid. So then, based on this received signal and your local measurements, you will decide to change the local power consumption, and of course this will change your state and influence future decisions based on local measurements. So these give us minimal communications with centralized entity, and also in order to have a smooth response from our population of the loads, we are relying on randomized policies, and this is somewhat similar also what is, has been done in telecommunications in the distributed congestion control algorithms, such as TCP, for example, and many people here in Cambridge have worked on this around Frank Kelly, and so it's also a nice link with this work. So this line of work started by a thesis of Joanna Matthew, and then there are also many other groups that picked on this line of work, like Simon Tindemans and Goran Štrbec, and then also a group in Vermont, and Misha Chertkov also now studies different MDPs model for load ensemble control. So all this work has similar goals, but the actual control architecture and information needed for the control is somewhat different. So I will now briefly survey the control architecture we used in our work, and then move on to the optimal control framework that is main focus today. Is this clear so far? Okay. So I'm very happy that many people presented the frequency control throughout the workshop and even the talk just before, so I will not give more details about that, but just to give you the main idea. So we have some control mechanism that is based maybe on the frequency control or voltage control, whatever you are most focused on. And this will define our, so I will think of frequency here, and this will define our reference signal that will be starting point of our approach. Okay, and then this reference signal will, for example, be revealed in real time, and based on this signal and the actual measurements from the aggregate power consumption of our residential loads, we will send this signal zeta, that think of it as a scalar value sent at each time step. Okay, and we, in most of our work, we assume that we can measure the aggregate power consumption, or that we can do state estimation for this aggregate power consumption. We do not need any information on power consumption of individual loads. Okay. Initially, since this started with the idea of frequency control or balancing reserves, we were happy to settle with less. So we started with a goal that was passivity of, let's say, a linearized control schema. But ideally, of course, you would like perfect tracking, but this is not easy to achieve, and especially it's impossible to achieve, especially in online setting. We can, if we have some information, for example, some forecast on the signal, we can go beyond that and actually formulate it as optimal control problem. So, main idea on the control architecture, we will assume that the individual load model is most of the time we will assume that it's a Markovian dynamics, and this is we will focus on the finite time horizon, capital T, and so we have some nominal dynamics that is given by P0. So this is probability of a given trajectory up to time T. Yes?
Is that zeta the same for every load, or would it be distinct?
So far, think of it as a homogeneous pool of loads, and zeta will be the same for all loads. They all receive the same signal.
And the zeta is independent of the state of the load. It depends only on the state of the grid. Is that right?
It depends. It depends on the state of the grid, because it depends on the reference signal that is sent, but it also depends on the aggregate behavior. In aggregate power consumption of the pool of the loads, because, but not on the individual state of a given load. Thank you. Okay, so we assume that this nominal load model is Markovian. So, and here it's actually assumed that it's homogeneous in time, but this can be relaxed. We can have time-dependent dynamics, but important is that it's Markovian. Then we will change this dynamics based on signal received from the grid, in order to so here is our grid information, and we will our control dynamics will also be Markovian. But this time definitely time inhomogeneous, because it depends on the signals that are received at each time. Okay, so main question here is how I can go from here and design this parameterized family P zeta that I will use in real time to to modify the dynamics of each individual load. And here, as I said, we assume homogeneous population for now, and assume that there is capital N loads in the system. As I think this summarizes nicely, that there is the same signal that is sent to all loads, and we measure this aggregate power consumption. This is our individual load state of load I. We assume that we evolve in discrete time, and there is a finite state space for the loads, for example, on, off. It can be a little bit more complicated. You might have maybe on and then two different power modes, but it's finite. Then given this signal received and your current state, okay, it's on and off, but you also might want to include other information for example, quality of service reasons. And you can definitely we assume that you can measure this local state. And given those two informations, you will need to design transition probability matrix to jump to the next state, x prime. Okay, in order, once you fix this family, parameters family of transition matrices, then you can use mean field theory to analyze the aggregate model. But so this is easy because we have lots of theory to do that. But what is really difficult is to come up with clever choice of this parameters family in order to obtain nice properties for the aggregate model. And there is no single answer for that. It depends what is the application, what are your preferences, whether you want simple design or you want really the most optimal design you can obtain. So in order to fix the ideas, I'll just briefly present the simplest possible load you can control, which are pool pumps. Why this is simple? Because quality of service is very easy to respect. Basically, you need to let the so this is a pool pump that cleans the water, so it just has to operate a certain amount of hours per week. So very flexible load. As a state, you can take the current power mode, which is denoted by MT, and also in order to avoid cycling, we include the time that you have spent in the current mode, because if you just change the mode, the probability to change it again will be very low. Then there is a state transition diagram. So imagine that you are currently on and you just switched on. We forbid you to switch off again for a while. And then after a while, the probability to switch off will be higher. And so once you reach the a certain time duration, we are just forcing you to switch off, because otherwise you are consuming too much for the consumer. I mean, you don't want to have too high electricity bill, and the pool is already clean, right? So similar for the off states. Then once you have this parameterized family, then you can study the aggregate behavior using mean field approach. And so what you, the key ingredient here is the empirical distribution. We denote by capital N the empirical distribution that corresponds to the size of population, capital N. And as we really care about power consumption, this YTN will be power consumption of the aggregate if the size of population is capital N. And then as N goes to infinity, you can show very easily the convergence to the mean field model. So this is when there is no capital N, that means that we are at the limit of our mean field model. And so here the assumptions are very small. This zeta t has to be continuous function of the previous power consumption, and the family, parameters family, has to be differentiable with respect to zeta. That's all that you need to assure in order to have the convergence to the mean field model. Okay, and then since so what is a bit maybe not obvious, let me just go back for a second. This might look cleaner to you at the first sight, but it's not, because this zeta t induces nonlinearity in our dynamics. So in order to design nice control schemes, you can just use the classical trick in control theory, which is linearize the dynamics around the nominal behavior. And this then can infer good control strategies. So we just, in practice, we just use PI controller, and it worked fine. Okay, so back to the pool example. Quality of service is very simple. You just need to work a certain number of hours per week. Nominally it runs maybe, it depends on the type of the pool pump, 6 to 12 hours per day, so very easy to shift around. We assume in this example that there is a centralized entity, balancing authority, that can measure aggregate power consumption, but absolutely not the individual state of the pools. Okay, and this gives you there is a delay with with this. It's confusing. So this is what you obtain. So here in blue there is a reference signal, but the tracking in this example is very good, so you can barely see it. Maybe around extremes you can see that there is some mismatch. Here in green there is control zeta that was sent at each time, and the deviation from the power consumption of the loads from their nominal behavior is in red. So a very nice tracking, but you can see that there is some discretized phenomena going on, because the size of population is only 20 devices here. So it converges extremely fast to the mean field limit, because the dynamics is very simple in this case, right? So once you go to higher size of the population, and this is 300,000, then it becomes very smooth. Okay, so that was a simple example, because basically we can control everything. So there is no dynamics that comes from the outside temperature or usage of, for example, in water heaters, we need to take into account usage of when people take showers. The whole approach can be extended also to a part of dynamics that we cannot control. And one control design that is maybe the easiest to extend to uncontrolled part of the dynamics, and also even to non-Markovian dynamics, is myopic design. So I will present it in a Markovian setting, but it can be extended to a part of dynamics that is not Markovian. So the idea is very simple. Take the nominal behavior of the load and just tilt it exponentially with respect of the signal received. So once again, U is power consumption in a state where you want to jump, x prime, and this zeta is a received signal. So if zeta is positive, you are going to incentivize the states that have higher power consumption. If zeta is negative, I'm going to reduce my power consumption. And the fact that I'm doing multiplication with the nominal behavior assures me that I cannot jump to the states where nominal behavior could not go, right? So there is hard constraint here. This part here is just normalizing constant. And if you we apply this simple nominal, simple myopic design to TCLs. So in particular, think of water heater here. And here the state is composed of, again, power mode and the temperature at, of the water at NT. So we assume that power mode can be just on or off here. You have lots of disturbances here that you cannot control, such as ambient temperature and, of course, people taking showers. This dynamics of temperature of the water is much more complicated than just in the case of the pool pump. Okay, so first of all, there is a very very standard model for dynamics of temperature in the water heater. This is just a first order ODE that is given here. Okay, of course, this is a very simplified model of the dynamics, but it captures lots of nice behavior. And in particular, it does capture the fact that it will depend on the outside the temperature. You can also add usage that that is well, not very well represented here, but you can also add usage of the water here. F of t. Yes. So it is represented. The usage here is represented with f of t. And so you are basically at any time step you are going to have hot water that might actually go out of the water heater. There is a cold water coming in. This you cannot control at all. It depends on the user and in the house. And so this is our deterministic nominal model. And how this is controlled in the most of the water heaters, at least in US, is that this temperature follows the deadband control. So it has minimal maximal temperature, and if the temperature of the water reaches upper bound, then the water heater is switched off. Then it drifts towards the lower value, and then it's switched on again. So that's clear. So we need a stochastic model to start with. So we just slightly perturb this deterministic deadband control, and this is given by here by two cumulative density functions. for the temperature at which we are going to switch on or off. So as you can see, we are trying to stay as close as possible to this deterministic behavior, but with a certain small probability, you are going to switch off even before you reach the maximum temperature in order to be able to perturb it with our control design. Okay, is that clear? Then given these two CDFs, you can easily obtain the probability of switching on or off. Here it is given the probability of switching off that is based on the measurements of two consecutive temperatures that we have, and similar for switching on using the other CDF, which then give us the nominal behavior for our water heater that uses the information of the current mode and the temperatures now and at previous step in order to decide probability with which we are going to change the mode. So very simple nominal design. It's just probabilistic variant of deterministic behavior. And then you can apply the myopic design to this, which is very easy to compute. So it's just so this is the nominal switching probability. You just slightly tilt it with respect to zeta received, and when we have this zeta that goes to that is positive and goes to and grows, then the probability to switch on will be bigger and bigger, approaching 1 at the limit. Okay, very simple, naive design, but in practice it works very well. So these are this is the experiment we used. The data for the usage of water heaters was obtained from Pacific Northwest region, and then for the actual dynamics of water heaters, we had data from Oak Ridge National Lab for 35 days, 35 water heaters and 50 days, and this was used to decide the parameters of the nominal model of our ODE model, and these are the results that we obtained. Here we have nominal power consumption. So you can see that there are two peaks in the morning and a little bit more spread out in the evening, where people use showers and they start cooking. So this is a typical load response. When it's yellow, it's the water heater is on. So you can see that they stay on a very short amount of time. They perform very well. So they just need they have a big power consumption over a very short period, and then they're off for a while. So so this is our nominal dynamics. Now, if we apply the control design that we described right now, then this this is tracking performance, and this is the response of one load. You can barely see the difference, but there's a couple of new on periods that appeared, and some are shifted in time. And if you increase even further the needs of the regulation, then basically they will just stop responding when what you ask them is beyond their flexibility capacity, but at other times they will track very nicely. So it doesn't go wild, it doesn't start oscillating. Okay, so this was much more complicated dynamics than the pools, because you have real usage, but still we obtain good tracking.
What is the time on the x-axis? What is that responsible? Which time?
Sorry?
What is the time?
Time is in hours.
Hours. So that one slope is 1 hour? No, what is it?
So this, the whole, here it goes up to 20 hours. So you can, I don't know, it's like it stays on maybe for a couple of minutes maximum. So it's not.
Are you referring to the next slide?
I can wait.
What's the next slide you're referring to?
No, I'm referring to this. What is? It says that's the response. So I can't see over which time. I can't read.
Well, it's 24 hours.
It's yeah, it's 1 day.
So do those spikes correspond to the time when water heaters, most of water heaters come on, or what are the spikes about?
On which figure? On the left or on the right?
On the right.
On the right, so this it may be easiest to see to watch is the yellow parts. This corresponds to water heater is on. The rest of the time it's off.
So why does it go up and down?
So this is temperature of the water in the water heater. So once you switch off the water heater, the temperature will just slowly go down because of problem of isolation of the water heater, and then sometimes you have big drops in the temperature because someone is taking a shower, so it takes lots of hot water out and lots of cold water gets in, and then it gets up because you switch it on.
I get it. Look, see, this is 100,000 water heaters on the left.
That's why I'm
But on
asking.
the right is just the first water heater.
Just one water
Yeah,
heater.
just showing how
Yeah.
one
Okay.
water heater acts. Yeah.
Okay, that was the confusion. So this is, yeah, I said it maybe but too quickly. It's on the previous slide. This is typical load response, and this is tracking performance.
Okay, so if I look at one water heater, it comes on twice, right? Those are the yellow cones.
Well, it's like there's
That time, right?
but during that time, so it's maybe 10 times during the day, which.
Then I don't understand why it goes up and down after that. You know, like if you look after the time when it came on, when the water was consumed, time, why are there those spikes happening at the water heater? It is on, but very short time. How line? She doesn't see that.
Oh, maybe you don't see, but the actual vertical lines where the water heater is on. For example, there is one here. There is one here, and so it's very short time because there is no water usage at that time. Okay. Okay. This is another experiment that we actually try to see what kind of signals we can track. So you can provide ramping services very easily. But so here, red and blue are superposed. So the reference signal is red. Power tracking is in blue, and then in green here is the control signal that is sent to the loads. Okay, then we also played around with different type of loads, so with fast and slow water heaters and fridges. And here what is interesting is just to see that if you compare the nominal behavior, which is in red, and control behavior in blue, you really observe the shifting across time. Okay, so let me go to the new part. And so I will start by reviewing notions of relative entropy, and then state the control problem. We will use as a measure of distance between nominal behavior and the control behavior. KL divergence of two probability mass functions, and so here L is log likelihood ratio, and here so we assume that we have finite time horizon capital T, and we are going to consider the control problem that is composed of two parts. So there is a reward for following what the grid needs, and then there is a penalty for deviating from the nominal behavior. So for now, I'm going to keep this zeta fixed, and then we will see, just to review some ideas, and then we are going to state the whole optimization problem for finite time horizon. So if you keep this zeta fixed, then you can obtain a solution in a nice form that should remind you of myopic design, but here we have a finite time horizon capital T. And so then here this is nice, this is closed form, but then you actually need to look at the long time horizons. So one possibility is to approximate it with behavior when length of the time horizon goes to infinity, which gives also a problem that has closed form solution, and corresponds to the infinite horizon optimal control problem that is given by the Donsker-Varadhan rate function between two probability transition matrices, the nominal and the control. Well, I'm sort of running out of time, so I'll just tell you very quickly that the way how you can solve this infinite horizon problem is through eigenvector formulation, and this is due to Todorov in his NIPS paper in 2007. But this only works if you can control the whole dynamics. If you have a part of dynamics that you cannot control, then there is another approach that we developed that is ODE approach for macro decision processes. But so it still works, but the approach to solve it is different. Okay, so let me actually let me skip that. Just one comment is that when you look at the linearized behavior of the system around the nominal linearized dynamics around the nominal behavior, what you usually see is resonance around the nominal cycle of the load. Typical fridges, that would be 1 hour. Okay, so now the main part of the is the optimal control. So here, so far we assume that zeta is fixed, and now we will actually go back to the time-varying reference signal, and we will pose the design of the parameterized family as the optimal control problem that has still this KL part that measures the divergence with respect to nominal behavior, but quadratic part here really takes into account the reference signal. Is the objective clear? Then Here we assume that reference signal is known to us. So typically we will be able to take into account forecast information. And then, of course, as time goes on, your forecast information gets better and better, so you can just run the whole thing in using a model predictive control. Okay, so our optimization problem is this. So time horizon is capital T, and this is the reference signal, and new k is the marginal at time k of the dynamics of our load, and this thing here will give us power consumption at time k. So we assume again that the nominal model is Markovian, so if we look at back what we just saw, if you would take this weighting factor here to infinity, then this corresponds to the constant signal that is sent through time, and this corresponds to the problem that you can solve as eigenvector problem. And also, if you take this to be infinity, so basically you have hard constraints that you need to have perfect tracking. Then this was studied by Chertkov and Cherniak in 2017, but the problem is that the solution does not always exist, so you need to figure out what signals you can actually track perfectly. So if you relax it like this, then you can show that the solution always exists, and this weighting parameter will give you how important is your tracking performance with respect to the quality of service to the load. So how well you are, how close are you to dynamic behavior? Okay, so this also has a very nice solution, but here you will see these new things, beta star here. So in the nominal behavior, this used to be our zeta, and here it's something that we need to compute. And it turns out that this beta parameter can be obtained as a solution of a convex optimization problem, and well, basically you can take this thing here as denoted by gamma, and then you have constraints so that this thing here is equal to gamma. If you take Lagrangian dual formulation, then this beta star thing here correspond to Lagrangian multipliers of the dual formulation. So just to have some intuition about it, but you have a nice convex optimization problem you can solve, and then it actually has a very neat structure, because when if you fix these values for beta, and then for whatever the beta vector it is, so you can also look at the twistor distribution of the same form as for the optimal. And what this gives you is the new Markovian dynamics. So not only for the optimal beta, but for any value of beta, we can define that. And this, for a given beta, I can actually compute iteratively what should be the transition probability matrix that will realize the solution to my optimization problem. And so this is how we can do that. So as once you fix what the value of beta is, then the key is to compute these AK values, which can be done iteratively starting from the end of the time horizon backward in time. And then this will give you the probability transition matrix that then you will apply forward in time and then move on. So it's this nice structure of forward-backward solution that that is very. I mean, you are usually very happy when you obtain this in mean field models. Okay, so I will just give you some. Okay, so if I'm, I can actually. So I will work in an algorithm with these AKs, but it's nice to interpret what is going on. You actually have forward forward dynamics on the on this density functions for the aggregate of the loads, but you have backward dynamics on the log likelihood ratios. So it's very intriguing, and there are things still to be studied here. And so this is sort of the picture, just summarizing what we just said. Okay, let me then just go to some numerical results and then computational issues here before I conclude. So we actually I told you it's a very nice convex optimization problem. So you can solve it. There is a forward-backward structure, and what I kind of put under the carpet is that your time horizon can be of a day or many days, and your time sampling may be 5 seconds. So it is a convex optimization problem, but it's a huge one. And what is important here, that you have a mismatch between the actual observations you can make locally for your load and what you really care about. And because I only care about accurate tracking of the signal, so imagine that this is sent every 5 minutes to you. But then I can react on 5 seconds based. So why should I have all this information from my load dynamics? So one idea is to use transforms to capture the most important information of your local load dynamics, but still stay on the time scales that provide you good tracking. So just we will here just assume that we have family of functions that we will apply both to our reference signal and to our power consumption, and everything that is transformed will be denoted by hat. And now this gives us a simpler optimization problem to solve that now has well, time horizon capital N instead of capital T, and so you have same structure for the solution, but then the question is how I choose this family of functions so that I get significant complexity reduction, but still good tracking. Here is just to okay. Well, any ideas? Think about it. Think about it, and just if you want to have a simple idea is to have Gaussians around every hour, for example. What would happen with that? So while you are thinking about that, I will introduce a new question to think about, and then come back to ask you the answer. So we also started with discussing that there is different possibilities for information architecture. This stays valid here as well. So you can sort of have various trade-offs between what you are going to compute locally and what you are going to do at the centralized authority. So, for example, you can maybe do as most as possible at the balancing authority. So maybe you want to compute the estimate of the of your distribution of the population, and then compute these betas at the balancing authority and send it to everyone. But you might also want to actually do the same computation at the local level, and then run the estimation of the of your empirical density at the local level, knowing that all the loads are similar as you. But you can also do a crazy thing and assume that all the loads are exactly in the same state as you, and they start from the same state. So Dirac measures as estimates. And in that case, what you are actually solving is slightly different. So it becomes each load is looking at its own state. So this would divide the population of loads according to the initial state. And then you are actually going to solve this modified problem. Okay, so, but it turns out that even if you do that, at least, for example, we started looking into, you have a relatively fast coupling of this dynamics starting from various initial states. For example, here for the example of TCL, so here they are refrigerators. So here you have the initial states. They can be on 2 degrees up to maybe off 8 degrees. After only about 3 hours, their estimates of the density become quite close. And after 6 hours, you really cannot tell what was the initial state. So I'll skip that because I really want to ask you. So what happens in our quiz is a question. Remember, we just chose these transform functions to be. We have 24 hours. I'm going to take one bell curve for each hour, and then apply the transformation, and what will happen. These are refrigerators. They have cycle of an hour, so this is our nice reference signal, and here is what happens. Not really what we wanted, right? But once again, this was the extreme bad example that took into account the resonance frequency of the load that we studied. If you actually take just every half an hour, you obtain this. And this is with this weighting factor, that is 100. If you increase the value, then tracking becomes much better. Okay. Okay, I'm going to the conclusions. So, as you can see, we can use a very simple control design that can be easily implemented today. This was myopic design and, for water heaters, and we obtained very good tracking. On the individual load level, it is very it is almost unnoticeable how power consumption changes. There are many computational challenges around this new optimal control design. For example, around transforms, how to choose good transforms. For the maybe there is another way to deal directly with the convex optimization problem. So I really invite you to join the this project. Then there are lots of engineering questions. For example, there is there are nice links between this KLQ optimal control design and LQR, and so this might give some leads to explain why we were always seeing passivity in our previous designs. So this is another big open question in this engineering question. Of course, there are questions around the actual nominal model design, whether, what is the right trade-off between quality of service that is included in the model, and you can just always do opt-out option. So if quality of service is jeopardized, you just decide not to implement the next switching of the power mode. Okay, and so then there are lots of economic questions related. So how to actually put this into practice? What is capacity of flexible loads? What is the cost that is associated? And especially if I'm giving different reference signals to the loads, what will be their cost and what is benefit for the system? So then there are network issues, and so far we were thinking of transmission network, but there is also distribution network. Can we help both of them, or helping transmission network actually hurts distribution network? This is something that we just started to think about. And there are lots of questions about markets, but Sean will be giving a talk tomorrow, so I'll just stop here.
Given that we started the session 10 minutes late and we've already eaten 10 minutes of the break, I think let's hold the questions, and instead, if you were about to raise your hand, come up front and ask them, and let's go out to the break, and we'll be back in 20 minutes for students.